Hello and welcome to Fun with Physics with Uncle Bob. This week I'll be taking a look at the third Lewis Carroll problem in my series of videos. My first two problems I presented were difficult problems and no solution was given by Lewis Carroll to these two previous problems. Indeed, my solutions are original with me as far as I know. This third problem today, Lewis Carroll did give a solution for, and I will be going through it with you and showing you how to solve the sorties or problems of this nature. Here is that problem. It's problem number 60. It can be found online through free public access to the book Symbolic Logic by Lewis Carroll. It's on page 124 in the online book. There's also available in paperback the book Symbolic Logic, parts 1 and 2, edited by William Bartley. In that book, this problem is on page 175. So go ahead and pause and read this problem. Then I'll go on to the solution. The solution to this problem, as given by Carroll, is if H, then A, or kangaroos are avoided by me. Let's see if that's true. This is my solution written in Power Basic. Doing this allows you to quickly solve Carroll's problems of this nature. At the top, we have all his variables or conditions as he defined in the problem at the bottom. 0 meaning negative, false, no, not, 1, positive, yes, true, etc., as I've defined here. So what this program is doing is looking at all possible combinations of all these variables to see if all the problem statements would be fulfilled. Here is line 1. Line 1, when translated to Carroll's notation, reads, if E, then C. There are two principles of logic to test here. The first is if E is positive or 1, C must also be positive or 1. The second principle is if C is negative, 0, then E must also be negative and 0. So this portion of this line will test the first condition. If E, then it must be C. But if we have C0 with E1, then we know that this condition is not fulfilled. The second thing to test is right here. If C is negative or 0, we know that E must also be negative or 0, but if we find E equal 1, then we have failed. So either of these conditions will fail the first statement. We test all the statements here, go on down. If we have a failure of 0, in other words, if none of these have failed, then we go ahead and make a notation and summation of the number of times we've gone through this program with a success of all statements being true. It's that simple. This is the rest of it. I'll go back to the top if you want to pause and copy. There we go. Let's go on and look at some output. I'll go ahead and run that now. It's done. Here at the top we have a total of 12. 12 meaning we had 12 runs that were successful. In other words, 12 different combinations of all these variables that resulted in a successful run. A successful run, meaning all the problem statements were fulfilled. The thing to notice here is a sum is the sum of the total numeric values of A, the sum of all these 12 successful runs. Same for B, C, D, and so on. In other words, we had 11 times for A where A had a value of 1. A had a value of 1 11 times since we had 12 runs. What that means is once in this 12 runs, A had a value of 0. Just once. That's significant because the fewer the runs, the longer the chain of logic that it took to get there. So what we're looking for is a run of only 1 for any of the variables here that were successful. So looking down here, we'll say A had a value of 0 only 1 time. That's significant. Looking on down here, we see H had a value of 1 only once because its total, H sum, is only 1. Once did it have a value of 1? 11 times it ran as 0. So what we're looking at here is an A with a value of 0 and H with a value of 1. So what happens when we input those parameters back in our program? Let's run it again. We'll run A with a value of 0. All the other variables or conditions, we'll try both states of variables here. I will run it. Here it is. Notice we only had 1 successful run when we set A to 0. The significance is when A is 0, H must be 0 too. So remember that. Not A implies not H. You might recall that our second condition that we found was a value of H equal to 1. So let's do that. I'll set A back to 0 or 1. We'll try both states as all the other states here. We'll go to H and set that value to 1. Run it. Only 1 successful run. H, as we said, is set to 1. A is 1. So what we have here is H implies A. H equal 1, A must be equal to 1. The previous run, we had not A means not H. That is the equivalent logical statement. This statement, again, can be interpreted forwards and backwards in the correct manner. If H, then A. If not A, then not H. So if H, then A. If not A, then not H. That is the solution to this problem. That's all for this week. We'll see you next time on Fun with Physics with Uncle Bob.